My name is Ian Johnson. I'm product manager for ARM's Cortex-M3 and Cortex-M4 products. And I'm here today to talk to you about some of those Cortex-M products and SecurCore, which is based on the ARM Cortex-M processor range. So if we start off with what ARM does, ARM is essentially a licensing company of IP. So we don't manufacture anything, or we manufacture very little. We manufacture some development boards. But our main business is in licensing IP to over 900 companies who then create their own special products based on that IP. And the whole range of ARM semiconductor IP available ranges from small microcontrollers, so sub 50 cents price point, operating at perhaps tens of megahertz, right up to 2 gigahertz processors at a much higher price point, multi-core. And soon, as you've probably seen announced, we'll move into 64-bit ARM cores. So a really quite wide range of products available from ARM in terms of soft IP. So if we look at what ARM does as a business, you could sort of think of ARM as almost like an outsourcing company. So many of our semiconductor partners find it more efficient to take an ARM design rather than doing their entire design in-house. And in fact, in many cases, many of these companies have got their own internal design teams designing competing products. So perhaps two parts of the same company, one with an ARM-based solution, one with a non-ARM-based solution. And within that business model, there are a variety of licensing models. So going right from an architecture license where a licensee is able to do their own implementation to support the ARM instruction set, through subscription licensing, so they're able to take, it's a sort of a all-you-can-eat model where they're able to take any number of pieces of ARM IP, through individual licenses, so a license, say, for a Cortex-A9 or for a Cortex-A15, for Cortex-M4, etc. And part of that business model is they pay an upfront license fee for the license in the first place. Then when they're actually shipping product, they pay ongoing royalties on the number of parts that they ship based on ARM IP. And there's really quite a long pipeline, if you like, in this business model. So right from the early research for a new core from ARM, through development, we're really looking at several years before we start seeing ARM IP, a particular piece of ARM IP appearing in the marketplace. To give you an example, some of the early designs, ARM7 TDMI, ARM9, is still a substantial royalty provider for ARM. We're still taking royalty in very large numbers. And you can see from this slide here that the growth in recent years has been quite phenomenal. So there were over 8 billion ARM chips, ARM-based chips, shipped in 2011. And over the last 5 years, that represents more than a 25% year-on-year growth. So ARM actually began in Cambridge 22, 23 years ago with a group of 12 engineers, and from that base has grown to the world's leading semiconductor IP company, with offices pretty much throughout the world, in the States, on the West Coast, in Austin, in India, in China, in Japan, and in Europe. And pretty much every semiconductor company which manufactures chips to go into the mobile phone industry has adopted the ARM architecture. We've got more than 95% of the mobile phone business, but as you'll see in later slides, that isn't the only, those aren't the only markets that ARM processors go into. And in fact, not only is ARM licensing semiconductor IP for processors, but also the libraries which go to make those processors, tools, services, and so on. And over the last year, if we look at the growth in the markets that ARM is shipping into, growth pretty much across the board, but just trying to pick out some interesting points from this slide. You'll see there that embedded, so anything ranging from processors that go in coffee machines. There are coffee machines that are based on Cortex-M3, through cameras, washing machines, fridges, point-of-sale devices. So anything where the core itself is not apparent has grown 70% in 2011. So really quite a rapid growth in the embedded segment. Yeah, yes.
What is automotive?
Automotive we count in embedded. So this is a somewhat arbitrary split of segments within the company. So there are teams looking after each of these segments, and automotive appears in embedded. And the interesting point to note on the licensing and royalty slide is that traditionally ARM has been seen as a mobile phone chip company, and indeed in terms of royalties from 2011, mobile still represents the lion's share of royalties. But if you look at last year's licensing activity, you can see that the licensing for embedded is pretty much identical to licensing for mobile. So we'd expect to see that in future years those royalties will become more evenly split between embedded and mobile. So if we now look at the inside of a typical smartphone, in terms of ARM processors, ARM technology within those phones, we're not only talking here about the apps processor being an ARM processor, but also ARM technology going into a variety of other devices in the mobile phone. So for example, Wi-Fi and Bluetooth chips. In fact, one of the widest shipping Cortex-M devices is actually in a Wi-Fi Bluetooth combo chip that ships in mobile phones. The baseband processor, often based currently on Cortex-R4, and as protocols become more complex, we'll see the adoption of Cortex-R5 and Cortex-R7 into cellular modems. In many mobile phones, the touch screen controller is based on a Cortex-M0, perhaps, or on a Cortex-M3. Some of our partners are producing power management devices, power management chips for mobile phones based on perhaps Cortex-M0 or Cortex-M3, running the DVFS policies to ramp the voltage and frequency of the main processor. The SIM has often got a SecurCore ARM-based processor in. So within a typical mobile phone, or within a smartphone certainly, you could find maybe 7 or 8 ARM devices, which explains to some degree the sort of the sheer size of the volumes of shipments of ARM processors. But the important thing to note is it's not all just about mobile. So, for example, in automotive, it's one of the big growth areas for ARM. In fact, we're already becoming a dominant player in some of the components of a car. So there are many Cortex-M devices in airbags, in chassis control. Some of the higher end cores are beginning to be used in infotainment systems. And indeed, as the consolidation of functionality increases, there's a need for more and more processing power within the car, within one device. So perhaps where you previously had a core that was dealing purely with an infotainment application, maybe it's now also driving the rear camera for reversing on a larger car. And that's all driving a need for standardization and safety and reliability. And so ARM is very actively involved in adhering to standards such as ISO 26262, which will become an increasingly necessary part of the automotive industry. Turning our attention now to Java. So there's really been quite a long history of Java support within the ARM architecture. So Java's been running on our ARM 7 and ARM 9 range of processors right through ARM 11 up to Cortex-A8, Cortex-A9. And those cores have hardware acceleration capabilities for Java, so you're able to execute bytecodes directly in the hardware. For example, on the ARM 926, and that technology has been carried through onto the Cortex-A family of processors. I'm sure there are many more reasons why Java is important to ARM than the ones listed on here, but just picking out a few examples, Java is critical in a number of the application areas where ARM is dominant, so in mobile phones, in high-end digital TVs, in Blu-ray, so able to execute Java apps on those devices. But increasingly, as I say at the bottom of this slide, we're seeing Java move into more traditionally sort of deeply embedded applications on ARM-based MCUs coming from our silicon partners. So if we look at how the industry is moving towards 32-bit Cortex-M devices for MCU. So the idea of this slide is it shows how traditional 8 and 16-bit architectures are no longer able to cope with the sort of complexities needed in the MCU marketplace. So whereas you once just had a serial comms channel, you've now got USB, Bluetooth, Zigbee, a whole range of communication protocols which need a more powerful processor, which need a 32-bit processor. In terms of display, we've gone from 7-segment displays to more complex displays, needing more power from the underlying processor to service those displays. and in terms of motor control, something like 50% of the world's electricity is consumed by some sort of electric motor. So being able to execute more intelligent algorithms to control those motors through field-oriented control algorithms, or being able to efficiently implement Park and Clark transforms to monitor and to control the operation of those motors, leading to a more efficient energy consumption, is something that's becoming key. And talking about power consumption, being able to have more complex algorithms running on a microcontroller, able to intelligently control the power usage of some larger device. As I mentioned before, safety is becoming increasingly important, and perhaps it's not such a sort of well-known fact, but the Cortex-M processor range is incredibly reliable. It's the Cortex-M3 was launched in 2005-06. We're now on revision 2 of the processor. It's currently the Cortex-M3 and the Cortex-M4 have just one very minor defect, which is never seen in compiled code running on the on the Cortex-M cores. So an incredibly reliable history for Cortex-M processors, considering that there are 2 billion of them in the world. We'd have known by now if there was a serious problem, I think. And going from a world where it was all about low-level control of a device, to sophisticated libraries that get you quicker time to market, and just in general this transition from traditional 8 and 16-bit processors out to 32-bit is all driving the need for Cortex-M cores. And so I've tried to sort of do a bit of a mix of business side and technical side. So if we look now a little bit more at what that technology brings, you can see from the graph here that there's really a significant growth in the last 3 or 4 years in 32-bit MCUs, with 4, 8 and 16-bit remaining reasonably flat over that same period. And much of that spike and much of that growth is based on ARM Cortex-M processors released by our silicon partners. And so I'd just like to go through sort of why that trend is happening. So Cortex-M processors deliver exceptional PPA, so high performance, low power consumption, small area. So perhaps surprisingly, programs compiled for 32-bit ARM are often physically smaller. They take up less memory footprint than many 8 and 16-bit architectures. And we're now down to single-digit microwatts per megahertz in terms of dynamic performance on Cortex-M, and down to nanowatts of power consumption for when the processor's in sleep mode. But those are still delivering, 1.25 DMIPS per megahertz on the Cortex-M3 and M4, and 0.9 DMIPS per megahertz on Cortex-M0. So very powerful processors consuming very small quantities of power. A very wide available clock frequency range. So we've got partners who are running cores at maybe 10 megahertz, right up to being able to run in a 40 nanometer process, perhaps run the core at 600 megahertz. So a very wide range of available clock frequencies. And coming with the core, there's a very rich debug and trace capability, not found in many MCU devices. So the ability to control the processor through JTAG or through serial wire debug, so just a 2-pin interface to control the core, and a very rich trace functionality which is non-intrusive on the execution of the target application. So you're able to collect trace data without interrupting the operation of the core. It's a large, flat, single address space, so 4 gigabyte address space. No need for the sort of old world of segment registers and the like. It's 32-bit. Many of the internal operations are work to a 64-bit precision, and they deliver a fast and low fixed overhead in terms of responding to interrupts. So, for example, on a Cortex-M3, there are just 12 cycles between when an interrupt happens and when the first instruction of your interrupt handler is being executed, since most of the work is actually done within the core itself. So all of the interrupt prioritization, stacking of registers, unstacking of registers when you exit from an interrupt handler, all handled by the core itself. And so just over the last year in 2012, we've seen a very wide variety of Cortex-M cores come to the market. So ST with their STM32, F0, F2, F3, F4 products, so building quite a substantial family of processors, where each member of that family has its own particular range of capabilities. The beginning of 2012, Silicon Labs launched their Precision 32 cores based on, or processor families based on Cortex-M3. So they bring a rich set of, their rich set of peripherals, which they were previously using on 8051, onto ARM Cortex-M cores. So Atmel recently launched the SAM4 based on Cortex-M4. So going together with their Q-Touch technology, so for touch applications. Energy Micro, so very low power Cortex-M implementations. Infineon with their XMC 4000 range based on the Cortex-M4, so now going more into industrial automation. In Japan, Fujitsu with FM3, so also based on Cortex-M3, they brought out a wide family of cores, so 210 new individual devices based on Cortex-M3. And of course Freescale with their Kinetis family, using the Cortex-M devices, but also in Vybrid, where they have a Cortex-A5 running, a rich operating system perhaps, and then a Cortex-M4 for more real-time critical operations. So far this year, and these slides get very quickly out of date because these numbers increase, but there are more than 350 new Cortex-M based devices out this year. Again, this next slide, slide 14, speaks to that broad MCU portfolio. So these are the logos of our partners who are currently actively shipping cores based microcontrollers based on Cortex-M cores, and the numbers in brackets are a sort of snapshot of the number of available family members in each of those MCU families. So you can currently choose from, I'm sure that number is now bigger, more than 1,400 products that are based on Cortex-M. And that silicon partner community has shipped a considerable number of MCUs over that period. So this is just MCU shipments based on Cortex-M. So this is not counting Cortex-M devices that are used as companion processors. So this doesn't count, OMAP or whatever, which uses a Cortex-M as a companion processor to offload some of the work from the Cortex-A. This is off-the-shelf MCU shipments, which now cumulatively have reached around 2 billion for Cortex-M devices, and those the shipments of those devices is growing in all segments. I've mentioned the names of these processors. These just show them as a sort of coherent set of processor cores. So they have one. The whole sort of message behind this is that they have one architecture with an upwards compatible instruction set, all with the same programmer's model, ranging right from traditional typical 8 and 16-bit applications right up to higher-end MCU requiring some sort of digital signal processing capability, single instruction, multiple data, hardware floating point, and so on. But all based on that single architecture. Yes?
I'm not an expert in CPUs, but do you have anything specifically for security? Because security
Yes.
keeps coming up with each and availability.
Yeah, so it comes sort of a few slides on. So I mentioned instruction set. So if we look at Cortex-M0, Cortex-M0 is pretty much entirely 16-bit instructions working on 32-bit registers. So it's still a 32-bit processor, but the size of the individual instructions held in your memory are mostly 16-bit. And then building on Cortex-M0 is Cortex-M3. So Cortex-M3 has all of the instructions that are in M0, but it adds a whole load of 32-bit arithmetic operations, bit field manipulation. And the idea here, this is the Thumb 2 instruction set, is that an intelligent compiler can find an appropriate blend of 16-bit versus 32-bit instructions, depending on whether you're optimizing for size or for performance. And then further, the Cortex-M4 adds a whole bunch of saturating arithmetic, of SIMD operations, so being able to perform a number of arithmetic operations in a single instruction across multiple data. And also an optional hardware floating point unit to accelerate applications that need a fast and accurate floating point capability. And so across all of these cores, there's the Thumb 2 instruction set. They all have what's called a nested vectored interrupt controller. So this is an interrupt controller that's built right into the core, whereas on older ARM cores, our partners would need to build an interrupt controller basically of their own on the outside. Nested vectored interrupt controllers built into all Cortex-M cores. They're all operating on a 32-bit address space. They all have a number of sleep modes, which I'll explain in a moment, and all have a sophisticated debug and trace set of features based on our core site debug architecture. So nested-vectored interrupt controller deals with interrupts from a variety of sources. So interrupt requests coming from peripherals, or a non-maskable interrupt, or interrupts coming from the built-in systic timer. And I mentioned just briefly before that all of the setting up of the machine state after an interrupt is handled in hardware, allowing you to write your interrupt handlers entirely in C, or in a high-level language. So you don't need to have prolog and epilog assembler, which loads registers and saves registers back to memory. That's all dealt with by the hardware, as well as prioritizing one interrupt over another, allowing a higher priority interrupt to interrupt a service routine currently executing that's servicing a previous interrupt. The memory map, because it's a 32-bit core, is 4 gigabytes of linear address space, and that address space is split up amongst code, SRAM, peripherals. Up the top is the system region for debug. So that's actually split up by what's called the bus matrix that's built right into the Cortex-M core. In terms of sleep modes, so all of Cortex-M cores provide this range of sleep modes implemented within the core itself. And then we allow basically hooks for our partners to add their own power management and sleep policies around those sleep modes. And these are all built around the concept of clock gating and power gating, which is built right into the design. So parts of the core can be entirely powered down. The clock can be only operating for part of the core, so hence the word gating. So you're controlling the clock signal going to parts of the core, or power going to parts of the core. And even if you have what's called state retention capabilities, you can have special flip-flops that are retaining the state of the system even when it's powered down, allowing you to wake up quickly through the wake up interrupt controller. Just to sort of finish up on the low power features, another feature of the core is sleep on exit. So the blue square on the left represents the processor running at full frequency. It then executes a wait for interrupt or wait for event instruction, goes into sleep mode, and then perhaps an interrupt happens. The interrupt service routine is executed, and if you've got the sleep on exit bit set, the processor automatically goes back into sleep mode on exit from the interrupt handler. So further saving you power. And indeed, because it's the 32-bit processor, you're able to do more work in less time. So actually your need to be awake during the interrupt handler is shortened. So I just briefly mentioned the wake-up interrupt controller. So this allows you to have basically two power domains. So an always powered domain where the wake-up interrupt controller sits, and perhaps the rest of your core held in a low-power state retention mode, allowing you to bring the processor up from its state retention mode through the wake-up interrupt controller. I will get to the secure cores in a moment. So built on that technology are two cores that I'm product manager for. One is the Cortex-M3, one is the Cortex-M4. And built on those cores are a further set of ARM IP called SecurCore. So we've noticed the need for smart cards, the need to keep data safe, keep your biometric information safe, PIN safe, password safe. And normal processors don't offer protection against sophisticated hacking, so they don't protect against someone who's actually able to monitor the power consumption of the core and draw conclusions about what instructions are being executed, or being able to physically tamper with the core. So the SecurCore range of processors is based on the Cortex-M architecture, but it's tamper resistant. So without going into the details of how that works, it's essentially that built right into the RTL is the notion of not being able to observe from outside which instructions are executing based on the characteristics of the core. And that's servicing a smart card market which is rapidly growing. Historically, it was dominated by non-ARM architectures, but now ARM is certainly moving into that area.
Will that find its way into M series someday?
That's an interesting suggestion. So I guess all I can say, current Cortex-M cores don't have a trust zone-like capability. That doesn't mean that they never will. Yeah. Or something that achieves the same goals as trust zone, so being able to operate in secure and non-secure modes.
The keynote today was talking about banking, and you got me thinking,
Yeah.
it makes sense to have an extra layer of protection at this level.
Yeah. So we've thought the same thing. So SecurCore family is called SC, so SC 100, 300, 000. The 100 based on ARM7 TDMI, SC 300 based on Cortex-M3, and SC 000 based on Cortex-M0. So now I'll talk a little bit about standardization. I mentioned that all of these cores have many similar characteristics. And to promote this sort of commonality, ARM has worked with a number of partners, so those are listed there, so they're silicon partners and tools partners, to develop a number of abstractions, if you like, on the core. So SIMSYS, the Cortex microcontroller standard, the software interface standard, is essentially a set of C header files which define a set of common capabilities across processors and across tool chains, regardless of which vendor those processors or those tool chains come from. And from the it's not always popular with some partners because they want to sort of create some lock-in to their core, but from an end user point of view, it's very valuable. It allows you to move very easily between Cortex-M based microcontrollers. And many OEMs are themselves creating software standard platforms, of which a couple are seen on these two slides, 31 and 32. I just wanted to say a little bit about the much used term Internet of Things. So essentially machine to machine communication. This slide 34 shows the idea is that this little girl is brushing her teeth. There's some sort of image recognition in the mirror that realizes it's her, and give some sort of feedback as to how long she's been brushing her teeth for, and so on. I'm not entirely sure that's a particularly realistic example, but it shows a sort of possibility of lots of sort of connected devices. And I guess the next slide, which is a bit of an eye chart, confirms that really the Internet of Things is many, many, many different things to different people. So, for example, you may be talking about sensors, so intelligent energy management, security, monitoring. In a motor control application, you may be talking about preventative maintenance, so being able to actually sort of essentially maintain the motor over the air, and monitor the performance of that motor. In medical applications, with on-body wellness tracking monitors, asset tracking in hospitals, in large organizations, and then all of those things that are currently not connected. So, anything from sort of street lights to traffic signs to, dare I say it, to parking meters to vending machines. All now being connected together and requiring some level of connectivity. And indeed, there are suggestions that over the next few years we'll go from the current 12 billion or so internet connected devices, perhaps to 1 trillion by within the next 13 years. And why ARM is a sort of favoured solution in this sort of area is that as software complexity grows and the need to execute more complex algorithms but still maintain low power consumption, then ARM is very well placed to provide solutions that give that capability. You're able to run more complex protocol stacks on a 32-bit architecture. That we've got a very large ecosystem of partners who are providing the software solutions on the ARM Cortex-M cores. So looking briefly at some microcontroller applications, it's all about energy use, reducing cost, increasing safety and efficiency. And in terms of energy consumption, if we could increase the intelligence of the appliances that are in your home, making sort of smart choices of their own, that's not only going to benefit the consumer, but it's also going to benefit the society as a whole. And currently there are only around 8% of meters which are automated. Certainly from discussions that we've had with our partners, this is an amazing business opportunity. Many of our partners are going into this area of intelligent meters. Also in medical, I jotted down some sort of statistics here. Apparently in the US there are currently 34 million senior citizens. That's projected to be 74 million in 2025. Apparently 1.2 billion seniors worldwide. So the requirement for sort of health monitoring and intelligent devices for within medical applications are certainly growing and creating opportunities for ARM devices. So another set of possible application areas. So servers is an area that perhaps, with the emergence of 64-bit ARM, you could see servers powered by ARM 64-bit processors, but also actually performing the power control of those servers. So some of our customers are interested in using not only ARM processors for the server technology themselves, but smaller cores, MCUs, for controlling the power usage of those servers. Now, I'm sure you've seen in some of Oracle's presentations the launch of Java ME, latest version of Java ME embedded for ARM-based MCUs. So that's something that's real now. Our partners that I listed on previous slides are now producing products that are capable of supporting Java, and the whole Java environment has been optimized and shrunk to a size that now really makes sense for entry into those MCU markets. And obviously, this is all backed by Oracle's long-term history of Java. Yeah. Yeah.
Does that extend here, or can it, or will it?
Big Little, yeah. So Big Little, as we're using the term, currently applies to Cortex-A cores because they've got all of the Snoop control capabilities. So you're able to have coherent caches across different processors. There are Cortex-M partners who are producing sort of a Big Little setup with Cortex-M. So there's an NXP part which has got a Cortex-M4 and a Cortex-M0. They're not quite executing in the same way as a Big Little cluster in the Cortex-A space, but the concept is the same. So you're able to, maybe run a complex DSP algorithm on the Cortex-M4 and, maintain some peripheral through the Cortex-M0. So there's certainly the same concept. It's not necessarily using exactly the same technology. Yeah. So in Oracle's Java ME, they're targeting a target system which looks very similar to those Cortex-M systems that I showed earlier. So an M3 or an M4, and then a number of peripherals. And there's still plenty of scope for scaling up to bigger platforms. I did say ARM doesn't actually manufacture anything, but one of the few things that we actually make that's physical and tangible are development boards. So, for example, there's one that's based on the STM32 microcontroller. So that's an evaluation board that comes from ARM's Kyle division. It's got quite a large 2 megabytes of RAM, 8 megabytes of flash, and a number of interesting peripherals, so touch screens, accelerometers, a joystick, gyroscope, etc., which will become a really powerful platform for Java development. If linked to a tool set like the Java SDK, so we're now seeing realistic cases of people developing Java applications and being able to load them onto a microcontroller board to trial their application on a development board such as the one from from Kyle. So I sort of rushed through a bit to the end there to fit in the available time, and we had a couple of questions as we were going along. Happy to take any more questions.
You mentioned display persona earlier. So what are your plans for this as a GPU? More traditional.
So ARM has its Mali GPU technology, which goes alongside the Cortex-A cores. I didn't mention that anywhere in this particular presentation, but there's a whole family of ARM-based GPUs called Mali, which are developed along with our intelligent interconnect, so that you can take a Cortex-A core and connect it to a GPU, and that's being done in many current top-of-the-range smartphones, for example. Well, thanks very much for your time. Thanks for coming along. Happy to talk to anybody afterwards, but thank you very much anyway.